So this lab's about a couple things, namely friction and what's called mechanical advantage. Let's talk about friction first, in case you haven't got to it in class. The frictional force, we use a special little symbol, little f, for this. It's equal to, it's interesting what it isn't equal to. It depends on only basically two things, that is the surfaces that are rubbing or rolling or whatever across each other, and that's described by mu, which is the coefficient of friction. It's a number that never gets over 1 and is sometimes pretty small, point something, 0.0 something. The synovial fluid in our joints has about the lowest coefficient of friction, which is 0.00 something. So that's good for us. And it also depends on not the weight of something in particular, but the normal force. And we'll talk about that a little bit more as we get into the second part. So, pretty obviously, friction is fun. Okay. Now, so the first experiment we're going to do is we're going to set up this is the top of a table. We're going to put a board on it that's been sanded and varnished, so it's pretty smooth, and we'll put a block of wood, call it mass 1 or just mass, and have this hang from one of our smart pulleys to a weight pan. Okay, so again, the frictional force depends on the normal force and the coefficient of friction. The normal force is not necessarily equal to the weight, but here it is, because if we look in the y direction, and of course, there is no motion in the y direction, so obviously the velocity is 0 and the acceleration is 0. It's not moving in the y direction. And so we have the vertical force, which is the normal force. Let's draw the force diagram on mass 1, or the mass here. There is a normal force and the force of gravity. They are equal but opposite. In this particular case, there's also the tension in the string, and there's a little pulley here which changes the direction of the tension in the string to vertical. We'll talk about that in a minute. And again, because friction always acts against the direction of motion, it's in that direction. So this is our very nice little force diagram. You should always try to draw a force diagram on each body in every situation that you're using Newton's laws to analyze, because that is the key to figuring things out, and a key for you to see what's going on here, what are the forces and what directions are the forces, and resolving them in the components, which we'll deal with in a minute. So, but we have really no components here. We have vertical forces, horizontal forces, so that's it. So the sum of the forces in the y direction is 0. The upward force, if we just look at the weights here, we do have two masses, so I probably should draw a picture of the mass holder here, and of course there's a weight acting down and there's a tension acting upward. And the sum of the forces in the y direction is 0 because the velocity is constant. If I keep the velocity constant, then there is no net force, and this moves down at a constant speed, this moves across at a constant speed, so we're obeying Newton's first law, the law of equilibrium. It's kinetic or dynamic equilibrium. So the sum of the forces in the y direction is 0, which means that the tension and the force of gravity, the weight of whatever's on that pan, are equal but opposite in direction. So the pulley here simply transfers the vertical tension force down here into a horizontal force. And so we have, for the x direction, some of the forces in the x direction, we have, again, they're 0 because it's a constant speed. You're making it a constant speed as best you can. So the sum of the forces is 0, gives you the tension in the x direction plus the friction acting opposed to it, which means the tension and the friction are equal. So the tension is the weight the weight is the force here that you're talking about, and the weight and the normal force are the same. And so all you have to do is divide this mass by this mass, and you get the frictional force. You get the coefficient of friction. Sorry. So this is mu times n. So the tension is mu times n, and the tension is also mg, right? And n is the weight. We'll call this mass 2 here. Since we have two masses, this is mass 1, and it's mu times the tension, which is mass 2 times g, right? And so the coefficient of friction is mass 1 times g over mass 2 times g. And the g's cancel out. And the coefficient of friction is simply this mass divided by that mass. Very simple. So that's the first part, pretty easy. But again, I would draw just to be complete, things get more complicated than this. Draw a force diagram for mass 1 on the table. Draw a force diagram for mass 2 on the table. Their motions are related by this inextensible string, and then you can analyze the situation. And you can almost see it without doing all this analysis, so to speak, but it's nice to get in the habit of doing that analysis. Okay, again, keep in mind how fast you move that across the table at a more or less constant speed, at whatever that speed is, and then we're going to do this again and figure out the coefficient of friction a different way. So let's look at that. So we're going to then set the board at an incline. It's sitting on this table. Here's where you really need this lead brick to keep it from sliding. Again, we have the smart pulley up here and the edge of the table. Put it over the edge of the table. And so put this block on here. We're going to start it at the top, however. So there's only one mass involved. We're taking the string off of the mass that we used to pull it across the table with, and we're just letting it slide down the table. So it's going to go down the table at a constant speed. Okay, so we're not using the pulley, we're just letting it go down the table. So this angle is going to be an important angle to figure out. So this is held up at this angle by a rod, which we'll show you in a bit, and a ring stand. And so you adjust the rod up and down on the ring stand until you find the same angle, the angle, I should say, that gives you the same speed of this sliding down this block of wood. And of course, that should involve the same coefficient of friction. So this is another way to get the kinetic coefficient of friction. So let's figure this thing out. Okay, so this is more complicated. Now, we have one body. We can still call it M1 if you want. And we have the forces on it. Okay, so let's draw a force diagram. So here is the force of gravity, which is also m times the acceleration due to gravity, mass 1 times the acceleration due to gravity. We have friction. Friction, now, it's moving down this way, so friction is acting this way. It's always acting directly opposite the motion. And we also have a normal force. The normal force isn't the weight of this thing anymore. The normal force is normal, perpendicular to the surface where the friction is occurring. Okay, so we have this drawing here. Now, we have kind of a choice here, and maybe the best choice isn't so obvious, but since it's moving in this direction on the inclined plane, let's take that as not only the direction of motion, but the direction for one of our coordinates. And so the motion is down the incline, and so let's pick the plus x direction as down the incline. So let me draw mass 1 over here, and so this is the plus x direction, and this is going to be the plus y direction, of course, perpendicular to it. So the normal force is in the y direction. The frictional force is in the x direction. That's good. That's good news. But the gravitational force now, because we've changed our axes, which again turns out to be the best way to do this, has a component, and you know all about those from your force table lab, a component in the x direction and the component in the y direction. So we have to find those components before we start using Newton's laws and so forth. So let's take the gravitational force. We can call it mg if you want, or f sub g. And we have to break it into its components along the coordinate axes that we've chosen. Okay, so this is the x direction coordinate, and this is the y direction coordinate. So this is fgx, and this is fgy. Again, x and y are not vertical and horizontal anymore. They're along the incline and perpendicular to the incline. Now you can probably see that this angle here, which is actually the angle we're going to need, is the same as this angle down here. I mean, you probably learned in high school that two lines that form an angle which are perpendicular to two lines that form the same angle form the same angle. I'm sure I didn't state that very well, but I think you see that this angle here and this angle up here is the same angle as the angle down there. Okay, so we have this triangle, and it's a nice right triangle, of course, and so we can use sines and cosines. That is, we see fgx is equal to mg, or f sub g, let's just mg, times that's the opposite side, so that's a sine of theta. And fgy is equal to mg times the cosine of theta. So these are our two force components and our tilted axes directions. Okay, so the sum of the forces in the x direction is again 0 because it's moving at a constant speed, and so it's obeying Newton's first law. And so we can write the forces in the x direction, the forces in the x direction, in the x direction down, making the force go down the incline is f sub g sub x. I'll write it that way just to keep emphasizing the x direction. And the force wanting it not to slide down the incline, of course you can see from the force diagram, which is really key to figuring out what's going on here, is equal to the friction. And it's in the minus x direction. So I like to put, this is the sum of the forces, which means you add up the forces, and this force happens to be in the opposite, in the minus x direction, so I put a minus sign there. Instead of putting minus here, I'm doing what this says, which is writing the sum of the forces. That means this force plus that force plus this force and so forth. That one force here is in the minus x direction. Okay, if it's in equilibrium, those add up to 0. Okay, so I can put this, let's see, fgx is mg, we only have one mass, so mg sine theta minus the frictional force is 0, or the frictional force is mg sine theta. Okay, so we don't know what theta is right now. So let's take a look in the y direction, some of the forces in the y direction. Again, the y direction is this way, not vertical. So the sum of the forces in the y direction is, in the plus y direction is the normal force. That's equal to the normal force plus the force in the minus y direction, which is not directly in the minus y direction, is the component of the force of gravity acting downward. So it's minus mg cosine theta, right? Those add up to 0. because it's Newton's first law and it's in equilibrium. So the normal force is mg cosine theta. They're equal but opposite. So let's take a look at these two equations here. And let's take a look at the definition of friction again. The coefficient of friction times the normal force is equal to the frictional force. So I can see a plan here. If I put this in for the normal force, put this in for the frictional force, I get this equation. And interestingly enough, of course, G cancels out. And interestingly enough, the mass cancels out. So that says that, that if you have a big chunk of wood that's the same kind of wood that this is, or a small chunk of wood made out of the same material, which gives you the same coefficient of friction, it's going to slide down at the same angle. Okay, and the angle is, solving for mu, mu is sine theta over cosine theta. And sine theta over cosine theta, which you all know, I'm sure, is the tangent. So for the second part, at the angle here, the tangent of that angle is equal to the coefficient of friction. Don't make the mistake of taking the tangent of the angle. The tangent of the angle is, of course, y over x. So all we do is measure the height and the length and take the ratio of those two values, and that is the tangent, that is the coefficient of friction. So don't go pushing any tangent buttons. You've got the tangent by measuring this distance over this distance. And when we get to the apparatus, I'll talk to you a little bit more specifically about what's the best way to do that. So in this part, the tangent of the angle is the coefficient of friction. And of course, we're going to do this by letting this slide down at the more or less same velocity as as you pull it across the table in the first part. We also want to find that of course gives us the kinetic coefficient of friction, and we want to find the static coefficient of friction also. And we do that by very carefully putting this mass up here in any little jar of the apparatus. We'll send it sailing down the incline, of course, at a constant speed. And then what we need to do then is to perhaps even lower this a little bit so that that doesn't happen, and then gently raise this up, probably not with this post, with this rod, but just by hand. Raise it up until the mass spontaneously takes off, and then measure this angle. It's going to be a bigger angle because the static coefficient of friction is bigger than the kinetic coefficient of friction. And you know that, as I mentioned in the lab, from the fact that if you want to get something going, push a big box across the floor, you have to push it harder at first to get it going. Then you have to push it a little bit less to keep it going. That's because this number is smaller than that number. So you may find a 50% difference between the coefficient of static friction and the coefficient of kinetic friction. Okay, the last half of the lab basically has to do with the mechanical advantage. And as I explained in the write-up, mechanical advantage is actually a force advantage. So we're going to measure the mechanical advantage of an incline. The incline is also one of the three fundamental or basic machines that there are in the world. Incline, the pulley, and the lever are the three basic machines. Everything that you see that's a machine is made out of combinations of those various things. The screw is a variation of the incline plane, and you know you can tighten something really tight with a screw and a screwdriver that's going to stay together very tightly because you can apply a much bigger force to tighten things with a screw than otherwise. So the mechanical advantage, as I mentioned in the lab, is really a force advantage. you can increase or multiply the force by using a simple machine, and that's it's an advantage in that sense. So you don't get something for nothing, as I also write in the lab. For instance, let's talk about the incline again. If you pick a mass up from down here and you put it up on top of the incline, like so, that involves doing some work, and work is force times distance, and the force we're talking about is gravity, force of gravity. That's the force of gravity times distance. H is how high you raise it off the ground, and so this is the amount of work done by moving this mass from rest up here and putting it up on top of the incline from rest. Okay, that's the amount of energy involved, and then the force that's involved is, of course, that force there. That is it's called weight, of course. So, and you know that if you take an object at the bottom of an incline, and whether it's you slide it up or roll it up, it takes a lot less force. So there's a force advantage. For instance, if it takes a lot less, if it takes half the force to move it up here, as it would if you picked it up and put it up there, then you'd say the mechanical advantage is 2. It takes half the force, or twice as much force, looking at it that way, to get it up here against gravity as it does to slide it up or roll it up. And that's the kind of advantage we're looking for in the second part. Okay, so in the second part, we're going to set up the incline, and again, we're going to need to measure x and y. Y over x is the tangent of the angle, and that gives you, back in the earlier parts, the coefficient of friction. But right now, we're going to do something different here. We're going to have a cart with wheels. The wheels have a little bit of friction in them, and we're going to have our smart pulley up here, and we're going to pull this cart. We're going to pull this cart up the incline by adding weights, as we did in the first part when we had it flat on the table, but with a piece of wood. Here we have a cart. So the cart it has some friction in its wheels. There's a little bit of friction up here in this pulley, and we're going to need to know how much friction that is. We're going to have a sneaky way of measuring that, actually. So this cart, this pan here, has a mass of 50 grams, and depending on the angle, unless you put an extra 500 or 200 grams in the cart, it may just, this pan by itself may pull the cart up and accelerate it up. We're not launching carts today. We are moving carts up at a constant speed again, because we want this to be in equilibrium, a kinetic equilibrium. So this cart will be pulled up the incline at a constant speed. Again, note the constant speed and make sure it's as constant as you can get it. There'll be some variation on the way up. And then we're going to use that fact to apply the analysis to calculate the coefficient of friction here, and also the mechanical advantage. So let's look at the mechanical advantage first. Again, if the mechanical advantage is 2, that means the force you needed to pull up the incline is only 1/2 of the force you would need to pick it up and put it up on top of the incline. So let's see. We're going to be dealing with a theoretical mechanical advantage, actually measured 2 different ways, and a real mechanical advantage. And the real mechanical advantage, the difference between those two is that the real mechanical advantage includes the force of friction, which is, again, always working against you. The theoretical mechanical advantage ignores friction. So when I'm talking about the theoretical mechanical advantage, I'm going to put a little 0 down there to remind us that's with no friction. So this is the ideal or theoretical mechanical advantage. The real mechanical advantage, we'll just label that way, as friction. So those are the two we want to look for. We're going to find two different ways to determine this, and we'll check those out shortly. Okay, so let's just get back to our situation here. This actually is a much steeper angle. I probably should draw it more realistic. You'll see that when we look at the apparatus at a much shallower slope. Okay, so here's the cart. We're going to pull it up with some weights hanging over here, and with the extra mass in here, we're going to pull this up at a constant V, meaning it's in equilibrium. So, if there's friction, it's going to take a little bit more force to pull it up than if there were no friction. And conversely, this is interesting, sometimes friction actually does help you out. This is one of those cases. If we let it down the incline, friction is going to be acting against the direction of motion, so it's going to be acting up. So, in the case when you're pulling the cart up the incline, friction is going to be acting this way. And you're going to have to add more mass here to overcome friction, more so than if there were no friction. And on letting it back down, you actually have friction working with you, keeping it from going down faster. And so there's going to be a slight difference between the force needed to pull it up, we can call that tension, the tension force needed to pull it up, and the force needed to let it down. And the difference between those two is friction. So that's kind of the rough theory behind what we're doing in this part. So, again, we're going to need to set the angle to a certain, to any value. Don't set it at a certain value. Y over x is the tangent of the angle, and we want to set this at an angle of about 10 degrees. Okay, so you can punch in your calculator if you want what is the tangent of 10 degrees and try to set these to roughly that value. Use the exact value that you have for y and x, that is y over x is the tangent of that angle. Use that exact value and not 10 degrees. That's just a rough estimate. We're going to do it for 10 degrees roughly and 20 degrees roughly, but know exactly by taking y over x what those angles, the tangent of those angles, and therefore the angles are. You have to apply your arctangent button to get the angle from the tangent of the angle, in this case. Okay, so I'm not going to go through the analysis of all this, but just remember that we've got two masses, and this is not much different from what we talked about before with pulling the block. We have two masses. Here's our, this is mass 2, this is mass 1, and if this mass is, if there were no friction, if this mass here is half of this mass, then the mechanical advantage would be 2. If this mass is 1/5 of what this mass is, to get it to move up the hill, then up the incline, then the mechanical advantage would be 5. It's just that simple. And those are listed in your write-up, equation 5, I think that is. So I think it's probably time to go over and look at the apparatus and see what these different parts really look like and calculate them accordingly. So let's do that. Okay, this is the setup for part 1, and I've got it actually all ready to go. It's balanced, but so there's the mass hanging down from the pulley. That's mass 2. Mass 1 is the mass of the block, which you can measure on the balance. Okay, so I'll just show you that even if it didn't have any masses besides the the pan mass. There's just a few more masses besides the mass of the pan, which is about 50 grams. But if I just let this go, it accelerates across the table. So what I need to do, what you need to do, is add a little bit more mass to this so that doesn't happen. I've got 200 grams there. You can use 200, 300, whatever you want. I think 200 works really well. And it just turns out that I've got this balanced pretty well with maybe 65 grams. I didn't count that up, but 65 grams of mass there total. And whatever this mass here is mass 1, that's mass 2. Now, if I just give this a little bit of a push at the beginning and let it go, this moves across the incline, or the board, I should say, at a pretty constant rate. That's what you want. Now, maybe if I put another gram on there, it would move a little faster. But what I want is a pretty uniform speed across the board here. It's varnished. It's pretty smooth, so it's pretty uniform. So that's part one. So the ratio of this mass to this mass gives you the mechanical advantage. Gives you the coefficient of friction, the kinetic coefficient of friction. Okay, in part two, we take the string off and use this rod. Now, the one thing you need to be aware of is that this is kind of teetery. What you need to do is, this rod is not horizontal, so what you need to do is maybe turn this a little bit until you see that it's not teetery anymore. This is a kind of a crazy angle, but at least it gets the board so that it's stable. So now let's, I don't know how this is going to go. Let's try to slide this down the incline at the same constant speed. That's a little too fast. And furthermore, it's accelerating. So I need to reduce this a little bit. One way to do that is to lower that here. Let's try it again. It's a little bit slower than the first case, and it's a little bit less uniform than the first case. But that's pretty close to the overall speed that the block slid down the incline at. You might want to raise that just a little bit. For a small adjustment, you just push this whole assembly just a little bit that way, and that raises the incline angle a little bit. So again, there's some unevenness in the board, but that's maybe closer to the original speed. So, okay, this is the angle. I'm just saying this is the angle. So we need to measure the tangent of that angle, which is the rise over the run, so to speak, and we do this with our meter sticks. A couple precautions here is you probably never actually measured an angle before. So an angle is the intersection of two lines, and the two lines we're talking about here are the bottom of this board, which meets the table right over here, not at the brick, but a few millimeters in front of the brick. And then, of course, since that's supposedly a nice straight board, the angle you want to measure can be measured anywhere, from here or here or here. It's the same angle. So I would recommend the way to do this is to just put the meter stick up against the lead brick, and don't read the zero, because first of all it's not zero, but read, I would say this is maybe 4 millimeters, reading about 4 millimeters where the board actually touches the table. So again, you read that very carefully. This meter stick looks a little warped, so I'd get another meter stick so it doesn't do teeter-totter on here. So again, the angle is the angle measured anywhere is the same angle. And you might say, well, this thing's sliding down on the top of the incline, and so why am I measuring the bottom of the incline? Well, if you think about the geometry here, the bottom of the incline makes the same angle to the table that the top of the incline makes to the table. So it's the same angle. So you can measure it from anywhere, but measure from the bottom. This is where the bottom is the one line that meets the other line, which is the tabletop, forming that angle. So I've got these meter sticks cut off. I've got them cut off so that 0 really is 0. I've cut a couple millimeters off the meter stick. This meter stick is cut off at 50, and I'm going to assume that's exactly 50. It's a little risky, but and some of the meter sticks are cut off at 60 or whatever, so we can use that. So this one goes from 0, really truly 0, and the easy way to set this up is to let Mother Nature make it vertical for you. So all you have to do is read from where these two meter sticks join here to the top, which is something like 19.4 centimeters. And this reading here is, you have to, don't forget to subtract 4 millimeters or so from the fact that that's not at 0. It goes to 79.7 centimeters. So 19 divided by 79, that is the tangent of the angle. That is the coefficient of friction. Okay, so for the static coefficient of friction, if you can get this to not move, that's fine. And what I'm going to do is very gingerly raise this up without bumping anything until it takes off by itself. This is a pretty big angle. There. Took out by itself. It's almost twice the distance here. So that means the coefficient of static friction is probably more like twice as big as the kinetic coefficient of friction. So here you have to kind of hold this here, or your partner can kind of run this up to hold it in place while you measure the static angle. Okay, that's my suggestions for doing this part of the experiment. Okay, so here's the setup. I've got this pretty well balanced ahead of time. Again, I set this in and twisted this around so that the board is not wobbly and it's flat on against the table. And let me just give this a little bit of push because we're looking for the kinetic coefficient of friction here. So give it a little push and let it go up the incline at a constant speed. Well, that's not quite constant. So these little washer masses go down to 2 grams. So I'll give you a couple 1 gram masses that you can add to get it to the nearest gram. So let's put another gram on and see how much difference that makes. That's it. So that's rolled up the incline. It didn't accelerate. It didn't decelerate. The little push I gave it maintained a certain velocity all the way up. That's as good as it gets. So you just want to add up the masses that are down there and use your balance to weigh this. Again, assume all these masses are accurate to 1%. So however many grams they are, it's 1% accurate. Don't try to mass this 500 gram mass on that balance because it only goes to 200 grams. So the cart, you just need that for the cart mass and use the other masses plus or minus 1% for your masses. So now I'm going to take a couple grams off of here. I don't know how many. And let this now roll down the incline. Okay, I got to take more than that off. So I've taken off about 12 grams or so. And let's okay, it's a little bit fast. It seems to be accelerating. Let me put 1 more gram on here and see if we can get it a little bit better. Make sure this that your cart is straight. Okay. It's accelerating a little bit more. Let's try 1 more gram. And let's see how that goes. Okay, so 1 gram is the closest I can come. 1 more gram stops it. So whatever the mass is there with only the 1 gram mass is the mass needed. So once again, to set these angles at roughly 10 and roughly 20 degrees, I would find out what the tangent of 10 degrees is and come close to that. For instance, this is probably an angle of maybe 13 or 14 degrees. So that would be fine too. I just want you to measure 2 different angles. One of them around 10 degrees, one of them around 20 degrees. More than 20 degrees, it gets a little violent, a little exciting. So don't want carts flying around. So anyway, measure this, y over x. That's the tangent, whatever that is. If this comes out 13 degrees instead of 10 degrees, that's fine. Use the angle that you set. Do one for about 10 degrees and do one for about 20 degrees. Obviously, as you saw, I took some masses off to get it to roll down the incline, and the amount of mass I took off was only maybe 10 or 12 grams. So the friction is very small, but you'll see if you do the analysis. Well, let me show you that on the board. Okay, so here is the analysis for the last part involving the forces needed to move the cart up and down the incline, each at a constant speed. Here's a case for pulling it up the incline. Here is the force diagram. Of course, there's tension pulling it up. There's friction acting down the incline against you. As always, we're going to label our direction of motion as the plus x axis for this motion, this body that's only moving in the x direction. And the weight, of course, is acting straight down, which means, such we talked about before, we have to resolve it into components that are along the incline and perpendicular to the incline. Actually, both of these are in the negative y and the negative x direction, right? Okay, so here's the picture. Here's the force diagram. Some of the forces add up to 0. Again, there's no motion vertical to the incline, so only motion is in the incline direction. That's the x direction. So it's the force upward, T sub u, minus the gravitational force that's trying to pull the cart back down the incline. That's minus m1g sine theta, as we learned before. And the friction force is acting down the incline also, so it's in the minus x direction. So here's the x component equation for the motion in the x direction, which is the only motion there is. Now going down the incline, we see that the force of friction changes direction. Everything else is the same. The force of friction is up the incline if the cart's going down the incline. So some of the forces in the x direction, once again using the direction of motion as the positive x direction, is this now becomes down the incline, which is the positive x direction, minus the force up the incline, that's the downward tension force up the incline, and also minus the frictional force, which is also up the incline as the cart is going down the incline. So these are the 2 equations for the 2 different situations. All right, now if we add these 2 equations, we see that because we've changed our x direction, the mg sine theta terms cancel out, And if I solve this for the frictional force, it's twice the difference between the force needed to pull it up the incline and the force needed to leave it go down the incline. It's half that difference. I'm sorry, it's half the difference. So if there were no friction, it would be the force exactly in between here. In fact, let's take a look at that. If we were to subtract these same two equations, let me rewrite this with the minus sign applied to every term, so you can kind of put this in parentheses in your mind. This is this expression rewritten with the minus sign, which is multiplying all those terms out in front. So if we subtract these same two equations, we get T up plus T down, the tension up down, minus 2 times the downward component of gravity. And if we divide both sides by 2, we get that the average of the up and down tension, literally we average out friction. So this is what we used to call T0, the tension in the rope and the string without any friction. And in fact, if you go back to look at equation 9 in the write-up, this is the definition of the ideal or frictionless mechanical advantage, the weight of the body divided by the force needed to move it up the incline, which is T0 if there were no friction. Also, prior to that, I did the calculation, which I didn't talk about here. That is, this is, if I put in m1g sine theta here, the m1g's cancel out, and I just end up with 1 over sine theta. That is also, believe it or not, the theoretical mechanical advantage at this angle, which you need to measure. We talked about how to set that and how to measure that. So we have 2 ways to come up with the ideal frictionless mechanical advantage: 1 over sine theta, as I just mentioned a minute ago, and also mg1 over T0, which is the average of the up and down tensions, which literally averages out friction. Okay, that's it.